All right, Chapter 8, Section 5, we're looking at rhombi and squares. Rhombi is the plural for rhombus. And this is the end of the parallelogram line. Here's what I mean by that. Here is a diagram that kind of gives us an idea of what the quadrilateral family tree would look like. So it starts up here at the top with polygons, kind of general, and of course quadrilaterals would feed into that group. And from quadrilaterals, we branch off into three subsections. All right, obviously you could just have your general quadrilaterals, which would stay here. Then if you want to get more specific, we have three groups. The parallelograms, which we've dealt with, and of course those branch off into either your rectangles or your rhombi, and then of course those go into being squares. All right, squares would feed into both those groups. That's one path. Another option is to do what we call kites. We're not going to deal a whole lot with kites, but let's kind of touch on it. A kite looks something like this, just as its name would suggest. And what makes it special is that the two pairs of adjacent sides are congruent. All right, and they have a whole set of issues related to that. But again, just in general, that's what they are. They've got interesting aspects dealing with their diagonals, how they interact. They're kind of like a rhombus in some ways. Not at all, but in some. And then this final group, which is a truly bizarre group, is the trapezoid group. And we'll get to those in our next lesson, but just a quick preview. Most of the time when people hear trapezoid, they think of a shape like this. What makes a trapezoid different from parallelograms is that there is exactly one pair of opposite sides parallel. So for example, the top and bottom in this case could be our parallel sides, and then left and right are just sides that are there. Again, that's a general trapezoid. When we're talking about isosceles trapezoids, we take that to yet another level. Not only do we have what we just saw with the trapezoids, but then these other two sides are the same length, hence the name isosceles, those two sides being the same length. All this to say, this is the family tree. This is how they're all related, and we've only been down this branch so far. So remember, anything that was true of a parallelogram is true for rectangles, and we're going to see that same issue today with rhombi and squares. So let's get into it. What are our definitions? Because we said definitions are everything. What are our definitions for rhombus and square? Well, if we're talking about a rhombus, our definition is this. It's a quadrilateral, so there's the first part, right? That we have four sides. And the second part is that those sides are then all congruent, right? That's it. That's all it means to be a rhombus. And from that, we can generate lots of other ideas. For example, this means that they're parallelograms by default. Notice we'd have opposite sides being congruent. So they are parallelograms. So anything that we've learned about parallelograms also applies to rhombi. Again, plural for rhombus. For squares, we have a similar situation shaping up. Ha ha ha. First is that they are quadrilaterals, so they're four-sided. They also, second idea, have four congruent sides. And third idea, they have four right angles. So notice, this means that squares not only are parallelograms by default, they're also rectangles by default and rhombi by default. So everything we've learned about all these other groups applies then to the square. But remember, while all squares are parallelograms and all squares are rectangles and all squares are rhombi, that's not true in the opposite direction. Something to think about. So let's get to it. Some theorems for our rhombi here. First theorem, the diagonals of a rhombus are perpendicular. So here's a quick rhombus. And again, they are rhombi, they are not diamonds. Right? This is not geology class. No diamonds, please. So there we are. The diagonals are perpendicular. So for example, B to D and A to C here, these are perpendicular. So how do we prove that? Well, one option is to look at what we know about isosceles triangles. So for example, let's kind of re-diagram this up here. We've got B and A and C, and of course we've got our diagonal going through here. Notice that A and C are the same. All right, again, that's just the definition of what it means to be a rhombus. So we have an isosceles triangle. Notice also that, excuse me, notice also that with these triangles, right, we could talk about perhaps similar or congruent triangles in there as well. Not our issue, but we're trying to show that this is ultimately perpendicular. Well, remember, if this is a rhombus, then we know that the bisectors, or excuse me, the diagonals will bisect each other. So this portion and this portion are the same. Cool. So that means we've got congruent triangles on either side, which means this angle here on the left and this angle here on the right, made with our diagonals, have to be the same. Well, if they are the same and they're also a linear pair, ta-da, they're right angles. And of course, we could tilt that and do the same with the other side here and see, yep, they're going to be right angles all the way around. So again, informal proof, but it works. This is the converse, let me write that in, converse, of what we see above. If the diagonals, of course, form a perpendicular, wonderful, then the parallelogram is also a rhombus. So again, converse of what we saw above, not a big deal. Each diagonal, this is a good one, folks, make sure you hold on to this one. Each diagonal of a rhombus bisects a pair of opposite sides. So in other words, this BD as well as AC, they bisect those angles that they hit. And again, we can go back to this diagram to help us. Notice we said we could base these two triangles congruent on side, 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 right? They are congruent. So that means these angles here would then, of course, have to be congruent by CPC/TC. So if each one's congruent, making up the whole, therefore it's been bisected, and we can do that with the other corners as well. So again, with one simple diagram, things we know about isosceles triangles, in this case, we would have a perpendicular bisector. All those things that we've learned about before are coming back now, and again, the more of those things that we've learned and remembered, better off our life's going to be. On we go. To summarize, all right, this is a good one. Like, definitely look over this, try to commit its memory. Things we know about rhombi. All rhombus, or excuse me, a rhombus has all the properties of parallelogram. All right, so anything we've learned about parallelograms applies. All sides are congruent, diagonals are perpendicular, diagonals bisect the angles of the rhombus. Cool. Squares, and again, please notice there is a distinction here. While squares are rhombi, it doesn't necessarily go the other direction. Please be aware. So again, a square has all the properties of a parallelogram, all the properties of a rectangle, and all the properties of a rhombus. So squares are kind of our catch-all. Anything we've talked about thus far is pretty much fair game for them because they are part of everything, basically. So let's look at some examples here, and we'll move on. Take a look. Here's our diagram. We know it's a rhombus. Cool. We've got a 53-degree angle here with W, Y, Z. We also know that VW, where is VW? Right here, this distance is 3, so we'll write that in. X to V, where is X to V? Right here, make a line out, is 2A subtract 2. And Z to V, so on this side, is 5A plus 1 over 4. Cool. Now that we got all the given information, we can go from there. We need to find the angle of, or measure of angle, Y, Z, V. So this angle here. Well, again, if it's a rhombus, we know we've got a right angle here. And if that's 53 degrees, then we simply need whatever's left to get back to 90, because we've already got 90 of the 180 taken care of. So in this case, it would be, what is that, 37? 37. Looks good. All right. Find the measure of angle X, Y, W. X, Y, W is right here. At 53 on one side, it's going to be 53 on the other. So that one was easy. Remember, it's bisected. X to Z, where is X? X to Z is that full diagonal. We'll notice we've got those set up, so let's do a little algebra. Let's see. 5A plus 1. And notice we're dividing by 4 on this one side, so I'm going to go ahead and multiply the other side there by 4. So that would be 8A minus 8. Again, just to kind of simplify things, I don't want to deal with that fraction. We'll subtract 5A on both sides, so that's 3A. We'll go ahead and add 8 to both sides, so that's 9. So it looks like A is 3. Now that we know that, we can plug it into one of these and then just double it. So let's go ahead and we'll plug it in here. So doubling it would bring it to 4 times 3 minus 4. So that's 12, subtract 4, that is 8. Wonderful. And now we need X to W, so this side length here. Well, notice we just found what one of these sides would be, so let's diagram it over here just to make it a little easier to see. So we got X, we got W, and we've got, what is that in the middle, V? Cool. We need X to W, so this side here, that's what we don't know. We just found A being 3, so that's 6 minus 2, that's 4. We found this side length was 3 is given up, so that's a 3, 4, 5 right triangle, so 5. Cool. Easy enough. This last one, right, these get kind of weird. we've got the coordinates, and I purposely didn't put a grid on here because this time I want us to try it without having to plot the points. We're asked to figure out if we've got a rhombus, a rectangle, or a square, list all that apply, and explain what we found. So there's lots of ways to tackle this. One way, and I'm going to just sort of give us a loose diagram here. Again, just with coordinate grids, not specific, but close. So E, for example, is 1 over and 10 up, so I don't know, we'll put E up there. F is 4 over, somewhere in there. F, there we go. G, 7, 2, I don't know, somewhere in there. And then H is all the way up here somewhere, I don't know, like that. So play connect the dots here real quick, blah, 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 blah. There we go. All right, so we have options. One option is to try to get as specific as possible. So one thing we could do is try to find, let me switch colors here. One way to work this problem is to try to find the distance of the diagonals. Now what will that do for us? Well, if we know that the diagonals are the same amount, then it limits us to being either a square, potentially, right, or a, and I've just dropped my pencil, I can't find it. Oh, there it is. So it could be either a square or a rectangle. If it's not, well, then we've got other options. If it's a perpendicular, right, so if there's slopes or opposite reciprocals, then we know it could be a rhombus or a square and then not a rectangle. So there's all kinds of things that we could do here. One option is to find two adjacent sides, find their distances. For example, if E to F and E to H are the same, well, then automatically that means it's a rhombus and a square, and then we might have to do a little more work to see, well, is it still also a rectangle, right? So lots of different things we could do here to work through it. So in this case, what I think is going to be easy is I'm going to go ahead and find the distances of the diagonals and see what I come up with. So if I'm going from E to G, those seem to be opposites there. Let's see, the differences in the X's are 6, differences in the Y's are 8, so 6 squared plus 8 squared. Let's see, so that'd be a 3, 4, 5, so that would be 10 squared. So the distance from E to G looks to be 10 units in length. Cool. All right, well, let's find the other one here from F to G. So from F to G, that's a distance of, holy cow, that's 16 plus 12. So if we work that out, we'd have 12 squared. Well, let's see, that would be also another 3, 4, 5, right? Divided by 4, so that would be 20 squared. So that one, F to H, is 20 units. So, wow. Based on that, since the diagonals are not the same, that limits us in the idea of a square, definitely not that. Definitely limits us in a rectangle, not that. Potentially could be a rhombus. So the only one way to test that, not the only way, but one way to test that is to grab adjacent sides and see if they're the same. We could also grab opposite sides, see if they're the same, and go from there. So right now, definitely not a rectangle, not a square. Let's find the distances around. So from E to H, we've got, let's see here, that's 11 and 2. So 11 squared plus 2 squared. That would be 121 and 4. So the square root of 125. So that is, what did we say, E to H? Cool. So there's one side. Let's go E to F and see what we get there. So E to F, let's see, the distance there is 5. The distance there is 10. And sure enough, we square those, we get 125, square root of 125 for E to F. Cool. So it looks like those adjacent sides are working out. If we can find F to G to be the same, then we're probably pretty safe in that we're dealing with a rhombus. So let's find it. F to G, so the difference there is 11. Difference there is 2. Well, what do you know? We're seeing the same thing. So yeah, that works. And then our last one here, G to H. Let's see, the difference there is 5. Difference there is 10. Yeah. So opposite sides, actually, all four sides rather are all the same. So cool. By definition, it is a rhombus, and we don't have to go any further than that. But again, lots of ways that we could work that out and ultimately explain our reasoning. So expect to see problems like this. See which method works best for you. Do you want to look for slopes first, maybe midpoint distances? for those diagonals, what do you think would be the best to get you the answer the quickest? All right, and again, graphing it out doesn't hurt either, but that does take time to ultimately plot all those points. And if it's not exact, sometimes it's hard to tell, and then you still have to go through all the work anyway. All right, so we'll see you in class today. If you have any questions, bring them with you. Have a good day.